used as a form of protection in big flat plates, or protecting the sensitive vital organs within inside, big sternum, big cranium. There are long bones, irregular bones and flat bones. Now, the significance of the bone is that if you look at the radiograph, you see little flecks. They're called trabeculae, and what they are beams. And beams have got a special biomechanical property in that they can resist compression, being squeezed, tension, being pulled, and torsion, which is the purest form of shear force, and that's twisting. So right from the get-go, the base of the horse is built in response to the biomechanical demand that is experienced in the environment. The bone's made up of white metal. It's very strong and it's very light. And if you think about it, white metals are iron, calcium, magnesium, cobalt. All of those are metals that are found in the environment and picked up and metabolized. The long bones have got a cavity in the middle of them, a medullary cavity, and that's filled up with marrow and red blood cells. So it's a store for different properties and different functions within the body, and it also protects against disease. So the bones are an extremely important part of the function of the anatomy of the horse. We'll look at the skeletal system. So the front limb, scapula, radius, ulna, electron process or the elbow, the knee, accessory carpal, metacarpal 3, 2 and 4 attached to it, P1, P2, P3 and the sesamoids. And you'll see that there are a number of attachment points for tendons and ligaments within this structure. This limb is held to the horse's thorax, not through a joint, but through a muscular spleen. The pectoral muscles at the front here are part of the sling underneath, and on the side, which aren't painted in, we've got the thoracic ventralis, cranial and caudal aspects, and they hold the inside of the shoulder blade to the thorax, so it's held in a sling. It's not physically fixed there. So, right down, as you can see, right down at the bottom, this is our attachment. You'll all be familiar with the attachment of the vertebral flexor tendon 2P3. Now, the attachments of muscles and tendons, they are ramified into the bone with what's called Sharpie's fibres, and it's meshed in so tight that on occasion, when there are injuries and overload through strain, that connection is so strong that it will tear the bone before the tendon or the muscle will give way. Okay, so on the front aspect, we've got a superficial digital flexor tendon, and tendons, their function is tensile communicators. They're like little rods. They work in tension, they pull, they can't push, so everything pulls, and they're made up of collagen and elastin, which means they have got an amount of stretch, but their primary role, and they're very efficient at it, is to transform or transfer the energy, the chemical energy from feed and sunlight and water that's metabolized in the body, made in the muscle, into kinetic energy. So it transfers that force from muscle to bone. The muscles that you can see, and there's a number around here, they are, as I say, the powerhouse. They function, they're chemical, and muscles have got 3 primary functions. What they can do is they have what's called isometric movement, which means that they can tense, but not actually move anything. Then they've got eccentric function, which means they can tense, but they get longer. And they've got concentric movement, which means they tense and they get shorter, depending on what the function is. And an example of this, is that. This muscle mass here, which is the hamstrings, those muscles have got the ability of concentric and eccentric motion, and they need to do that because during locomotion it carries those 2 functions.
Could you read my concentric and eccentric?
Eccentric means that as it contracts, it elongates. And it can do that because of the way that it's made. You've got pendant types and you've got which are put together like a fan, and you've got, I forget the name of the other ones, but it depends on the space that that muscle's got to fill, depends on its structure, and it also dictates what it can and can't do. And concentric? Oh, concentric means that when it functions, it contracts.
I also heard the expression
Isometric?
Yeah.
Well, what that does is isometric, when it contracts, it doesn't move anything. It just tenses. Now, an example of that is the serratus ventralis muscles, the ones that hold this shoulder blade on there, they work in an antagonistic system. They work one against the other, push me, pull you, for stability. And there's a very low tension all the time, and that seems to be a isometric function. It tenses, but it doesn't actually move anywhere. It just holds it. So, yeah. Okay.
Yeah, perfect.
The muscles can pull and push at the same
No,
time, or
it can't
different muscles.
It can't push. That's the whole point about this. Muscles don't push. Everything pulls. It works in tension.
Okay, that's
See?
what I was thinking.
Yeah,
about.
that's why. Right. Yeah, that's why there's an antagonistic side, and I'll just demonstrate here the two sides of the flexor and extensor chains. So we talk about the extensor chain. Because the muscle, when the muscle contracts, the force that it generates moves in that direction. Towards the attachment. And what you see here is the predominant muscles that are to do with the protraction of the limb. There are other muscles on here, but because these are the ones we want to talk about. Okay. And you can see that the direction of pull when those muscles contract is upwards and forwards. Now, attached to the shoulder blade here is the supraspinatus muscle, which makes up part of this flexor extensor chain here. And if you notice that the shoulder blade is angulated, and that's a mechanical advantage, because when you place weight on here, this is going to automatically collapse if you think about it. You know, there's nowhere else for it to go but this way. And because there's an attachment from the shoulder blade right the way around through the biceps, the sertus fibrosus, and the extensor muscle mass and extensor tendon, what that does, it attaches just that part of the knee, locks the knee out. And with this horse being stood as it is, all these muscles here, they're tensed to support the limb. Now, so the limb doesn't collapse, there's another antagonistic function from the flexor muscles. And they're also pulling in that direction. And that works in an antagonistic way so that it stabilizes and it keeps the limb in equilibrium so it doesn't collapse. So, there's two other muscle masses that we painted on. There's the lats, work in that direction, and the ascender for the biceps. And what they do is they attach to the shoulder blade, and they're responsible for the movement of the shoulder blade during locomotion. Alright. So, we've talked about the muscles having attachments and attached to the skeletal structure, and it creates a lever arm. It creates a lever system. Now, biomechanically, there are three types of levers: class 1, class 2, and class 3. Class 1 being the most efficient, which means least effort needed to make them work. The class 2 is the second, and class 3 is the least efficient. I'll just give you a demonstration when everything turns up. In the meantime, I'll pass the hat round. All my own work. I used to be called Banks, but I've given up going on buildings now.
I don't think they know who Banks is.
No, they don't. front point, the loads at the end, the fulcrum point, you can see it as the bar, and the effort that's needed to move that, to move the load is the most efficient lever you can get. You'll all use this type of leverage at some point, whether you use a crowbar or whatever. That's the most efficient. The second most efficient is the wheelbarrow type. Fulcrum points at the end, loads in the middle, situated along the shaft, and the effort that's needed to, that's the second most efficient lever. And the last one, which is a class 3 lever, is the fishing rod, fulcrum point and efforts at the end, and that's the least efficient. Now in the horse, through development and evolution, the red muscle masses in the flexor chains, they are all class 2 levers. They've developed to have the second most efficient as possible leverage. On the other side, those in blue, they are third class levers. They are least efficient. But if you think about it, when the limb is protracted, it's flexed and it's taken forward. So the inertia is reduced. So it's developed to save energy and exploit as best as possible the mechanics that has been available to it to save as much energy as it can. Now, the movement of the front leg. We talked about in the stance phase, the extensor chain is on the tense and it drops its head as it starts off. The head drops down, which initiates the brachiocephalic muscle. This big muscle attaches to the head's a counterbalance, and it uses that cantilever effect. This muscle attaches to the forearm to start the process of locomotion. The flexor muscles flex the limb, and because of the attachments of the deep digital flexor tendon on the P3, the toe can be curled up, and because of the attachments of the superficial digital flexor tendon, there's two attachments at the bottom end and the top end of P1 and P2. The whole pattern can be curled. Now the reason that the horse, or any animal that uses its legs like this, that they flex them and bring them up, is to reduce inertia. Another biomechanical efficiency. If you think about it, if you walk with straight legs, the inertia slows you down. If you bring the bottom of that foot up closer to the centre of rotation, is what the horse is doing, and we do the same thing, that allows you to move more efficiently. And that's what that does. So during locomotion, the flexor chain flexes, and the extensor chain through the brachiocephalic muscles and the biceps extends the limb and retracts it, bringing it down and reducing acceleration to almost zero before it strikes the ground and it loads. The process of that loading is that the fetlock flexes, dorsiflexion, and the tendinous structures are stretched and they absorb that kinetic energy from the muscle. So energy, forces, they can't be dissipated, but they can be converted, and it converts that energy into the tendons and then releases it in the cranial phase as a horse moves forward, and it does that by tensing the tricep muscles and propelling itself forward, effectively bouncing off the front leg. Any questions so far? No? An extensor chain. Quadriceps femoris. Insertus fibrosus. Which are your quads. And there's some unique functions in here. The horse has been designed and developed to move at speed. So it's got long legs, everything in the middle of the bone's been absorbed. A lot of the digits that it did have disappeared. And this horse is able to lock its stance and save energy when it's stood still. And this process takes place because the hamstrings, the quads are attached to the top of the patella, and the patella is attached to the tibia by three ligament structures. There's the middle one, the inside one, and the outside. So medial, central, and outside one. And what happens is that this muscle, the surface fibrosis, pulls up. Tensor fascial artery pulls up this way, which lifts the patella, and the quadriceps and this biceps here pull the patella out of the way and unlock the limb. So it can be locked or it can be unlocked. Another unique function of this limb is to join these joints, the stifle with the hook at speed to synchronize it. There are two fibrous bands which attach from the femur to the top of metatarsal 3 and from the femur to the point of hook.
You need to demonstrate how that patella works.
Yep. If you watch, if you put your hand on it and you flex the limb,
Now it's locked.
yeah. You watch. There's the patella, and it moves, it locks. If you watch, it's lifted up and then dropped down again. That's how that works. If you put your hand on it and you flex them, you'll feel it. It'll go up and out, and up and down, back down again. Okay, so the reciprocal apparatus, which is the peroneus tertius at the front of the leg and the gastrocnemius, which is at the back and touches to the hock, synchronise the bottom of the limb during locomotion. Because this muscle mass, the hams, being the powerhouse, are the ones that flex that limb. Okay. So, what I haven't drawn on here, but one of the major muscles that contracts the hind limb is attached to the spine, just around about there, and attaches to the top of the femur, or bottom of the femur, and it's called the iliopsoas muscle. There's two attachments, one up here and one here, and that is the major function of the hind limb. And the first thing that happens during locomotion is that the pelvis is actually flexed, like that, and the limb's taken forward. Now the flexor chain, especially these hamstrings, they've got two functions, eccentric and concentric movement, so they can move in both directions. The flexor muscles of the superficial and the deep flexor tendons. So you can see the attachment from the bottom of P3 and the two, the P1 and P2 comes right from the bottom. So when the limb is flexed, the pelvis is flexed first of all, and then the limb is pulled or protracted forward. Then the extensor phase takes over. Now you'll notice, I've got it picked up, and that foot is actually at an angle. And the reason for that is that mechanically the tibial tarsal joint in the hock is actually set at an angle, and it's set at an angle for a reason, is that during speed the horse will kick itself in the gut because the limbs from the bottom move to the outside. Again, once the hind limbs come forward, it's then placed, and the powerhouse of the gluteal muscles, the hamstrings, using the efficiency of class 2 levers, propel the horse forward at speed. Okay. Any questions so far? You've got a ball or a bit of paper or a cup of balls. I need to throw it somebody.
Could you repeat the iliopsoas' origins and insertions?
The iliopsoas attaches to the bottom of the spine and underneath the pelvis, and it attaches to the femur.
On the inside.
On the inside, yeah. Now, if you think about this, all these limbs, they work independently. They can be, the front limbs can be extended and protracted together. They can be lifted independently of each other. Same as the hinds, despite the fact that the hind limb is connected directly by a joint, so you've got bone-to-bone contact. And if you think about the transfer of energy from this muscle mass during locomotion forward, a bone-to-bone contact is more effective than a muscle sling. Yeah. Okay. And a downward element. And if we impart a force to this cup, you'll have the forward element and the downward element. And you end up with a trajectory. But if we were to draw a line from the point of origin to where it landed, that is a combination of the forward and downward elements, and that's called the resultant vector. It's got direction, and it's got size, it's got magnitude, which means it is a force, and it can...
Here's a stupid question in this country. Who shoots? You know all about that then, yeah?
Yeah.
We don't do that in our country, by the way. Not allowed. But we've also got free healthcare.
We don't allow that either.
And because we come from the good old days, you know, when men were men and women were glad of it.
So where this is leading...
Oh yeah, where this is leading. Is there any single women here that want to be condemned to a life of servitude?
Force, vertical axis, gravity, which travels in straight lines, straight down to the centre of the earth, is acting on the shoulder blade, and it forces down. Because there's two elements, the arrangement of muscles and tendons direct the vector force down the centre of the column of bones to reach the shoulder. The arrangement at the shoulder then changes the direction of the resultant vector force down the humerus. And then at the arrangement of the triceps and the biceps directs it again down the column of bones, and that force, following the centre of the line of the bones, comes out and is directed through the centre of the foot at the point of force. It's all done by the ligamentous structures and tendinous and muscles. From side to side it does the same thing. So if you think about the force being directed down the centre of a straight limb, when it's got a bend in it, at the point of the bend, we say it's a joint, then any of the soft tissues that are on the outside of the bend are going to be under a greater pressure to try and keep that force centralised down the centre of the bones, because that is biomechanical efficiency. That's why you want horses with straight legs. Okay?
Fundamental laws of physics apply to everything in life. And certainly if you believe that the Americans went to the moon and not to Arizona, well, you see, he's laughing. He did go to Arizona, didn't he? Or was it down here with Lockheed? But anyway, fundamental laws. Weight falls in straight lines through the centre of mass. For every action, there's an equal and opposite reaction. And the third law, which sounds a little bit stupid, but 2 seconds, mate, I'll be right with you. Which sounds a little bit stupid, but is really pertinent, especially to us, is that if it doesn't look right, it's not friggin' well right. Okay, and that relates to those fundamental laws. Okay, it's important to us because most of the pathologies and injuries that we have to deal with are nothing short of repetitive strain injuries that are caused by deflections on those fundamental laws. The weight of this force through its skeletal structure is transmitted in 2 ways. By a bone-to-bone contact through the centre of those limbs until it hits the floor. And then there's a second force that's applied, which is the remote force from its body centre of mass. In the horse, the body centre of mass, if you take a line from the point of the elbow up to the point of the sacroiliac, come across the ribs, and then just behind the withers, it's about there. 60% of the horse's weight is on the front end. This is the load-bearing end. The third of it is up here, which is the cantilever. This end takes about 40% of that weight-bearing force, but is the engine room, which is why you see all these big masses of muscle here. The bottom of a horse's foot is the mirror image of the stress that's placed on it by fundamental law number 1. Whatever that looks like is a result of this and how it interacts with the ground. As the load's pushed down, that equal and opposite force is met by what they call a ground reaction force, which pushes it back. Now that sounds a little bit simplistic and makes you think that it's the ground that's holding it up. But what's actually holding it up is the push from the ground, but the judicious use of energy within this muscular chain to suspend this column of mass inside of this body frame. So there's a bit of tension on the tendons and ligaments and the muscles that help hold it up. That's the minimum amount of energy that it uses, but it suspends it in it. Okay? Now when you've got conformation defects of one form or another, one of these groups, plus the ligaments that are holding it together, is under strain. All of these red, blue structures, plus all of the ligaments that are not drawn on here, plus the hoof, have what are called limits of elasticity. In other words, they can bend and yield under strain, but they've got sufficient enough elasticity to return to their original shape. Strain is a resultant of force, which is mass times acceleration. So at a standstill, this 500 kilo specimen here is being accelerated down by 9.8 meters per second to the ground. Where was it going then? All right, yeah. So the strain is this force times over the time that it's being loaded. Now all of those structures have what they call a stress-strain curve that reaches their limits of elasticity. So they can be under strain for a certain period of time, then they reach their limits of elasticity, and then just beyond that, they reach their optimum strength. If it's still being overloaded at that point, that structure fractures and loses its elastic properties and becomes what they call plastically deformed, permanently deformed. Most of the stuff that you see is somewhere between the limits of its elasticity and its optimum strength. It's overstrained. And these days in particular, you see it with a lot of sports horses on different surfaces, and it manifests itself in the form of ligament strains. Diagnostic imagery and stuff. There's a higher incidence of collateral ligament lamenesses, suspensory ligament lamenesses. They're all to do with the physics of how this interacts with the ground under motion and that stress-strain curve. The deform, sorry?
I had a question, but going back a little bit to the center of mass on the horse.
Yeah.
Does it ever change depending on what the horse is doing, whether it's, let's just say if it's galloping or depending on
The center of mass is constantly mobile, okay, and it's affected. Remember I said that what it was is the force is mass times acceleration, and the acceleration is moving it over its supporting structure. I'll give you a demo. Come up here. Stand and face down. Meet Billy Joe Bob. Now, let me tell you about Billy Joe Bob. Okay, because Billy Joe Bob here, his job is a tyre fitter. Anybody here recently had the tyres done? Okay, so you know, Billy Joe Bob here rips your old wheel off, rips the tyre off, he's listening to his iPod, chewing his gum, thinking about Sophie, who he wants to be doing something to tonight, but he's certainly not concentrating on your truck. So then he puts this wheel on this little spinny thing and it wobbles around and he's really not paying much attention. And the little green light flashes and he reaches in his box and he gets up a little lead weight and he smacks it on the rim of your truck. Billy Joe Bob is the most important person in the entire smooth running of your truck. Because if he don't put that lead weight on in the right place, that wheel's wobbling, the truck pulls to one side, and instead of doing 18 miles to the gallon, it does 18 gallons to a mile. And you're already complaining about $3 gas. Imagine what that would be like if it was $12 a gallon gas where we live. So, his job, this moron, is responsible for your health and safety and your financial wealth. Okay? But, here's the thing about it. I told you there that his weight is transferred by bone-to-bone contact through his limbs down to the ground. His feet are roughly the width of his shoulders. So his base of support is also supporting another force, this remote action force, that comes from his centre of mass, which is about here, runs down through his navel, through his scrotum, and in between his feet. Now the muscles here managed to keep him stood up relatively comfortably. Comfortable there? Not bad? Yeah. Spread it out a bit more. So when I give Billy Joe Bob here confirmation, okay, and his base is extended for one reason or another, the distance between this centre of mass and the base of support is what they call a lever arm or a moment arm. And what that means is the amount of energy that's going to be required to affect turning it over. But because the base is extended, the musculature here is having to take up more strain because gravity is pulling on his scrotum and trying to pull it to the ground. And you'll see an instant reaction. But what's happening there, while you were like that, and you weren't there very long, you start to feel it pain down here and here in the centre of your knees, and then your ankles. That's what happens to that. Eventually, those elastic structures will break. Okay? And you'll have to try and compensate for that by changing his posture. Okay? And that brings me to probably the two most common expressions in horseshoeing that mean nothing but horse shit. Balance and support. If I ask any one of you now what you do about a certain condition, you go, well, I'll balance its feet and I'll give it some support, won't you? What on earth does that mean? Let me tell you about balance. You sit down for a minute and let me borrow you, boss. I don't think I'm you because you look a little bit like me. But we've got an excuse for got grey hair, that's what does it. When your hair changes colour, the molecules affect you. And this is actually solid muscle of a relaxed nature that can be put to use at a moment's notice. Well, 2 or 3 weeks and the foot pump out the car. Alright, balance is nothing to do with a static image. It's a dynamic thing. And it's the ability to retain stability with the minimum of postural sway, in other words, the minimum movement. So if I apply a force, what's your name? Jim. If I apply a force to Jim, and I push him, he has a little bit of a sway, but he's still pretty stable. If I increase the magnitude, or change the direction of that force, he has to move to maintain his stability, otherwise he's going to fall over. Okay? So that's what balance is. From a horseshoeing point of view, what we're trying to do is maintain that ability within these structures in any position, because it's dynamic. And because this is a quadruped, at times it's going to have to carry all of its weight plus on one of these feet. You can sit down now. Brings me back to this weight bearing thing, because we'll call this 500 kilos for easy weight. That means that basically, stood there square, it's got 150 kilos of weight being transmitted down his front limb and 100 kilos down his hind limb. At the walk, the physical load that goes through the foot, the front foot, is about 30% of that total body weight. But force is increased by acceleration. So when I change the gait to a trot, what happens is the amount of force or mass that goes through that front foot is now 110% of its body weight. So now instead of 150 kilos, it's 600 kilos. If you go to the gallop, it's 170%. So that's now 800 kilos on one foot, times gravity, 9.8 meters per second. In the show jumper, over 1.45 meters of about this weight, on the non-leading limb, in other words, the trailing loading limb, it puts through that foot the equivalent of 4.5 metric tons of force. That's all taken up by the structures in here. And then you wonder why the hell they deform. Yeah? But they're designed to take it, but for short periods of time. When you extend that time, you're increasing that stress strain curve. It collapses. Yeah, does that make sense to everybody? Good. So, when the next time you go to buy one of these, yeah, think about that. Can I borrow, let's borrow you, boss. Super. Yeah, you don't need them. And can I borrow your t-shirt? No. That's a great t-shirt. Turn around and show them. When you go to buy one of these, what I want you to do before you go is go buy one of these t-shirts. Take the t-shirt, put it over its head so you can't see its ears and its pretty nose. Yeah, there's them dark glasses of yours, mate. Make sure they're non-reflective one way, so you can't see its colour. And then just braille feel its legs, will you, for Christ's sake. Yeah? And we can avoid all this crap. Sit down there, thanks a lot. I love the t-shirt. Because lots of the issues that you face are related to this conformation. And you ain't never, ever going to be able to fix that. If you wanted to have any effect on that whatsoever, you should have been dealing with that from birth to 3 months below the fetlock, 9 months below the knee, and 18 months for Loriola. After that, you're peeing in the wind. And the truth of the matter is, most of these dressage wives and trainers won't have you look at one until it's 5, and they want to break it in and ride it and shoe it all on the same day. You think you've got to put a set of shoes on, you're actually being paid to brunk it. Are you done with that thing?
Yes.